Hello and welcome to this video where today we're looking at the Michelson Morley experiment, and these are the three things that you need to know. You need to know why the Michelson Morley experiment was done. We need to have a look at the experimental setup and how they performed the experiment and what they were looking for, and then in the end we need the results of the experiment. So the Michelson-Morley experiment all came about due to Maxwell's equations. And if you remember back to when we looked at the nature of electromagnetic waves, Maxwell basically said that light is an electromagnetic wave. And this, of course, caused slight issues because the scientists at the time went, okay, well, something's got to be actually oscillating. So, for example, if to have water waves, you've got to have water. To have waves on a rope, you have to have the rope there. In other words, waves have to have a medium to pass through. So they basically came up with a theory and said that light is oscillations in some sort of medium, and this medium is called the ether. So it's spelt in modern ways. It's spelt like that. You sometimes see it with an A on the front, but it's still pronounced the same way. So it's the ether. So the ether was thought to be everywhere, and it was basically just sat there and didn't do anything, but things moved through it. So for example, it's very difficult to actually think about the ether in a three-dimensional kind of way. So let's imagine that instead the ether is kind of like a two-dimensional thing. And what you could do is, as the Earth moved along around the sun, it would be moving through this ether stuff. And the speed of light that Maxwell predicted, he basically predicted that the speed of light was the speed of light relative to the ether. So actually, if you're moving through the ether, the speed of light that you measure would be very slightly different, because if light, for example, was coming towards you like this, then it would be travelling at 3 times 10 to the 8 meters per second relative to the ether. If you were going this way, for example, then you'd be measuring the speed of light actually to different to the 3 times 10 to the 8, because you're moving relative to this ether stuff as well. So like any good scientist, they basically went, okay, so if this ether stuff is there, then we want to be able to detect it. And using this motion thing, we could do that. So there's an analogy to see basically how an easier way to think about this. So here we've got a boat, and the boat is on the sea. So here's the sea, and the sea is completely nice and still, and nothing is really happening. It's a really still day, so the air is, we can basically assume that the air is not moving. Now this thing here is basically a big foghorn. So this thing here will give out sound, and it gives out sound, and the sound in air travels the same speed in every single direction. So if this boat is still, what's going to happen is this horn is going to basically give out a sound, and the sound is going to travel this way, and the sound is going to travel that way. And these two people are an equal distance away from the horn, and so if the boat is sat still and it's a completely still day with no air movement or anything, these two people are going to hear this sound at exactly the same time. However, you could actually tell if the boat was moving, because if this thing was on a, again, it was a nice still day, but the boat was now moving in this direction, you then basically go, okay, right, we're going to sound the horn, and the horn would sound, and the sound would be emitted like this. But this boat is moving this way. So actually what would happen is that the sound would travel out from this in nice equal speeds, so it's the speed relative to the air, but the boat would be moving this way. So in actual fact, the person would be moving towards the source of the sound, and this person would be moving away from it. And so therefore this person would hear the sound first, and this person would hear the sound second. And so simply by looking to see if there was difference in the time, or if there was a difference to see whether one person heard the sound first or second, you could actually tell in which direction the boat was moving. And that's a little bit like if we go back to here. What you could do is if you had, for example, light coming towards you, and the Earth was going this way, then you can measure the speed of light. And then if the light was coming again towards you and you moving in the opposite direction, you'd measure a different speed. And so what you'd show is that the Earth is moving through this ether, and that the speed of light is a constant relative to the ether, but of course it changes as you move through the ether, as Galileo and Newton basically said. So what we want to do is basically want to replicate this thing, but for light. So this goes a little bit beyond the spec, but this is basically how they did it. Here you've got a light source. So this is the theory behind it. You don't actually need to know this for your exam, so you can always skip on to the next slide if you don't want to look at where it comes from. So here's a light source and it's giving light out, and we're going to consider one beam of light that basically goes this way first of all. So it's going to go from the light source towards this thing here. This is a mirror, and the light's going to come along to this mirror, it's going to reflect off, it's going to go back to the light source, and we're going to detect it when it gets back to the light source. So this is a light source and also a detector as well. And we're going to imagine that the whole piece of equipment is on the Earth, and that the Earth is moving this way through the ether. So you can imagine that, for example, as it goes around the sun at this moment in time, it's going this way here. Now we're basically not going to use the same numbers. The Earth travels relative, at least relative to the sun, the Earth travels at 30 kilometers per second. So that's only a value of 0.01% the speed of light. So any numbers we're going to get are going to be really small. So we're going to change it. We're going to basically assume that the Earth travels relative to the sun 10% the speed of light, and it's just going to make our numbers easier to basically to see. But it'll give us some idea of basically how you would do these calculations. So what's going to happen is we're going to shine this light out of here, and the distance this travels, and this is going to be parallel to the direction. So the distance this thing travels is going to be equal to, so the distance the light travels to get from here to the mirror is equal to, we're going to be the speed of light multiplied by the time it takes to get to the mirror, which is going to be t1. Okay, but if you think about it, the light's given out, and as the light takes a certain amount of time to travel to the mirror's going to move as well. And the mirror's moving at 10% the speed of light, because the mirror's on the Earth, and the Earth is moving at 10% the speed of light. So we can actually say that the distance that the light travels is actually equal to the 300 meters it travels here, because it's got to travel 300 meters to get to the mirror, but then the mirror's moved a little bit. And this mirror will have moved basically this distance, which is going to be equal to the velocity of the Earth multiplied by the time, which was for us would be t1. But the velocity of the Earth is 10% that of the speed of light. So we can write that as plus 10% the speed of light, so 0.1 c times by t1. So now we've got an equation. So we've got c times t1. So the speed of light times t1 is equal to 300 plus 0.1 c times t1. And we can rearrange that. And if we put our numbers in, then we actually find that t1, which is the amount of time it takes to get from here to the mirror, and the mirror's moved a little bit, is equal to something like 1.111 microseconds. We can do exactly the same thing because we want to detect it on its way back. Now it'll come from this mirror at this point, and it'll move back this way. But as it does so, this detector will catch it up. So it'll actually travel a different distance on the way back. So we can say that the distance it travels on the way back, which is going to be equal to the speed multiplied by the second time, is going to be equal to 300 meters, because the distance between the detector and the mirror is still 300 meters. But as the light comes back from here, the light rays caught it up, so we have to take away the distance that this detector moves forwards. So that's going to be equal to minus 0.1 c times t2. So we've got two times. We've got the time it takes to get to the mirror and the time it gets to get back to the detector. So obviously the total time it takes altogether, the total time is just these two added up. So if we put our numbers into here, first of all, t2 would be equal to 0.909 seconds. And so the total time is just those two things added up, and that gives you something in the region of 2.020 seconds. Now we can do exactly the same thing, but instead of going parallel to the direction, let's go perpendicular. And if we're going perpendicular, then really the there and back of the light, if you like, shouldn't actually be any different. So because what we're going to do is we're going to shine a light this way, but because the source and detector is moving this way, we're going to actually make a triangle. So this thing's the light's going to come out of here. We'll put a mirror up here, and then this thing will reflect off, and it will travel back down to here, and our detector will have moved this distance here. So we can make this into a little triangle like this. And if we kind of zoom in a bit, then what we've got is we've got a triangle like that. And so our detector's moving from here to here in the time it takes for the light to go up to the mirror. And then there's going to be a symmetric part here, and the time it takes to go from there to there is the time it takes to come back. Now this distance from here to here, so the distance from here up to the mirror, that's our 300 meters again. So it's the same distance, but this time it's perpendicular to the direction of the Earth's travel rather than parallel. So again, we can do exactly the same thing. If we think about it, this is just a triangle. So the distance from here to here is just c times t. The distance here is 300 meters, and the distance here is the velocity of our detector multiplied by the time. Again, we'll call them t1 and t2 on this side. So that distance there is ct2, just in case they're different. And this is the velocity of the detector multiplied by t2. So we'll think about just this one here. Now, just from Pythagoras, we can automatically say that ct1 squared, so that distance is equal to that distance, 300 squared, 300 squared, plus the vt1 squared, well, velocity again, so the velocity again is going to be 0.1c, because it's 10% the speed of light, so we've got plus 0.1c t1 all squared. And so what we can do is we can basically take this to the other side, and we can work out what t1 is, and if we do that, then we can show that t1 is somewhere in the region of 1.005 microseconds. And because this is symmetric and nothing's changing, then t2 is going to be exactly the same. So t2 is also equal to 1.005 microseconds. And so again, our total time is going to be just those two things added together, 2.010. Oops, there's a micro missing from that side, so microseconds on this side. So to travel 300 meters there and back, give or take, because this thing's moving, would take 2.02 microseconds. Perpendicular to the motion of the Earth, it would take 2.01 microseconds. So there's a difference in time simply because we're moving in this direction and we're not moving in this direction whatsoever. So there's a difference in time. And so actually, if you sent out two light rays, one in this direction and one in this direction, that were completely in phase to start off with, when they got back to the detector over here, they wouldn't be in phase anymore. So there would be a phase difference that you've induced because of that. And that's the principle that Michelson and Morley used to try and work out and measure the Earth going through the ether. So this is their experiment. And so they had a monochromatic light source here, so basically one frequency. So it was just one frequency or one wavelength of light. They shone the light along here, and they wanted two light rays, one that's travelling parallel to the Earth's motion and one that's travelling perpendicular to it. So they split it up, and for that they used this semi-silver glass block. It's basically a glass block, and it's got a silver part on this side. And when it gets here, some of the light's reflected, and some of the light is allowed to pass through. So it basically splits the light up into two. This light ray goes up to this mirror up here, so this is a mirror. It comes back through here, it goes through the glass block, and the light comes back through here, and this is a little telescope type thing that you can look through and you can see the light. That's a telescope. The light that wasn't reflected simply passed through here, it went through this glass block, and it came back along here. It hit the silver side here, and so it came back down here. So you split your light up into two and then recombine the light over here. Now, the important thing to say is the reason this glass block is here, it's not obvious, but this is the compensator. And the reason that that's there is because what we have to have the same optical path lengths. Now that doesn't necessarily mean to say not only do you have to have the same distances from M2 and M1, what you also have to have is the light has to go through the same amount of glass, because if you look at this one, as this light comes along, it goes through this part of the glass, so it goes through one thickness of glass, a second thickness of glass, it goes up here, reflects back down, it goes through a third thickness of glass, and then comes out the other side. For this light ray, if this compensator wasn't here, it would go along here, it would go through one thickness of glass, it would travel to the mirror and come back downwards. So you have to put this compensator in here to make sure that it goes through this light ray goes through the same thickness of glass as this one. So now you've got your Earth is travelling in this direction, and so what you should do is you should induce a phase difference, because although this is monochromatic light, it's given out potentially all of the lights in phase here, and then you get a phase difference when you look through your telescope. And when you look through your telescope, you see your concentric rings like this, so you see an interference pattern just like you did with electron diffraction last year. And so you've got these bright and dark fringes. And then Michelson and Morley went, okay, so just because we get an interference pattern doesn't mean to say that what we've got a phase difference induced. So they were then actually really clever. They said, right, okay, if we actually turn the whole thing round, so if we turn this round, so we turn it round like this, so M2 is now over here and M1's over here. In effect, what they've done is they've changed it round, so instead of the Earth going this way, so it's not doing that anymore, the Earth is travelling this way. And if that happens, then the phase difference will change, so it will be the opposite way around. And so what you'll see is your fringes will change position. And so if that happens, you would see something called a fringe shift. So when you look at when people talk about fringe shifts, what's basically happening is you're altering the phase difference between these two light rays simply by turning around, because now one takes longer to get there and back than it did before, and so the phase difference has changed, and so the interference fringe is changing, and that's what they looked for. So they did this, and they were really confident about this, because this is what should happen. So they should have seen an interference pattern, which were these concentric circles. When they rotated their equipment through 90 degrees, the fringes would shift, because basically the time taken by your two beams of light changes, so therefore your phase difference changes. And if your phase difference changes, then the position where the dark parts and light parts of your interference pattern are, they're going to change. And so they were really confident they could see this, because you could predict this. So they reckoned it would move by around about 0.4 of a fringe width. So here's your fringes like this, and there's a dark fringe, for example, and you can measure the width of this fringe, and they reckoned it would move by 0.4 of a fringe width. In terms of their experiment, they were really confident they could see this, because from an accuracy point of view, their experiment was accurate down to 0.05 of a change in the fringe width. So they were 8 times more precise than they needed to be in order to see this. So they were incredibly confident they could do this. So they performed their experiment, and they found absolutely nothing. There was no change whatsoever. They rotated their equipment round. The fringes did not move. That meant, if we go back to our explanation, that they rotated this thing through 90 degrees. The time taken by the two beams of light was exactly the same, so the phase difference remains constant, and so therefore your fringes don't change. So they detected nothing whatsoever. So there's only one thing that you can really predict from this. There are two things really. You can either say that the Earth drags the ether along with it. Well, if you did that, there would be other effects that you would see, and so that you can basically rule out. So the only conclusion that they could come up with was that this ether does not exist. And in actual fact, from an even more fundamental point of view, it meant that the laws of motion didn't apply to light. What it really meant is that light speed is constant no matter what you are doing. So that sounds really strange. So what it really meant is that when the Earth was travelling in this direction, when the light was being emitted, it was travelling at the speed of light. And when the light was coming back, it was travelling at the speed of light. The motion of the Earth made no difference whatsoever. So that's a second thing that was really important. Basically, the speed of light does not depend upon the speed of the source or the speed of the detector. The speed of light is a constant no matter what. So that was a Michelson Morley experiment in terms of what you need to know. You need to know why they did it. Well, basically they were looking for the ether. You need to know the experimental setup and what each part of that does, how the experiment was performed, and what they really expected to see. So this is what they expected to see. And the results of the experiment, well, the results were that they didn't find any change in the fringes at all, and so it meant that light is independent of the speed of the light source or the speed of the detector, and it meant that there was no ether. So that was the Michelson Morley experiment. Thank you very much for watching, and I'll see you again soon.